Our final keynote speaker today is Tirthankar Lahiri, who is Vice President of the Data and In-Memory Technologies Group for Oracle Database, and is responsible for the Oracle Database Engine, the Oracle Timesten In-Memory Database, and Oracle NoSQL DB. He has 22 years of experience in the database industry and has worked extensively in a variety of areas, including manageability, performance, scalability, high availability, caching, distributed concurrency control, in-memory data management, NoSQL architectures, and more. He has 27 issued and several pending patents in these areas. Tirthankar has a BTech in computer science from the Indian Institute of Technology and an MS in electrical engineering from Stanford. Please welcome Tirthankar to the stage.
So I'll talk about in-memory technology at Oracle and what we are doing with the in-memory stack for the Oracle database. So this is our view of what we think the next generation data platform should be. And this is actually a presentation in itself. Each box here could be a full 1-hour presentation. But I'm not going to take, 20 hours to present the slide. I will say the next generation platform needs to support all possible services, be built on an architecture that has in-memory as a fundamental component, in addition to things like multi-tenancy, security, and fault-tolerant scale-out. And we should be able to run this platform on uniquely optimized hardware, purpose-built for these workloads. And of course, this needs to run on clouds of your choice, whether it's cloud at your customer site or on the public cloud. So this is the broad vision of where we think the industry is moving as a whole, as where databases become platforms to do more than just the traditional database workloads that existed 2 decades ago. So the great thing about being at a summit for in-memory computing is that this slide is unnecessary. Normally when I do present to customers, I have to tell them that in-memory is important. But I think everyone here gets this, that in-memory is no longer some niche specialized technology. It's really a technology for today. And if you want to be a real-time enterprise, as Abe said yesterday, you have to be a real-time enterprise to be profitable in the future. So if you want that, then you have to be ultra-responsive. You have to have in-memory processing to make your decisions in real time. It's no longer something that's optional. And if you look at the systems we have today, where a standard 2-socket Intel server, not a supercomputer, has up to 1.5 terabytes of memory. If you run a traditional disk-based architecture on that platform, it's a bit like using Windows 98 on your latest laptop. Now, I don't think anybody wants to be that person. So it's a way to, you guys can all do this with me when you talk to partners, customers. Just tell people, spread the word that in-memory is a technology for today. We have to use it today to gain the advantages that you need to be viable companies in the future. So we get this in Oracle, and we think, therefore, that in-memory is a technology that belongs not just in one place, but in multiple tiers in the technology stack, in the application tier, in the database tier, and even in the storage tier. So in the application tier, we have the Timesten in-memory database, which Oracle acquired in 2005. It's been a while, and Timesten has been a very successful product at Oracle. It provides microsecond response times for workloads where response times and throughputs are critical. So I'll talk about Timesten very briefly. How many of you here are familiar with Timesten? Just a quick show of hands. OK, that's good. That's quite a fair number. Timesten is basically a standard relational database. It has asset properties. Your data is safe. If your database crashes, if your node restarts, it just recovers from logs and checkpoints, just like any normal database. It provides standard SQL, which is a big benefit for developer productivity. It's a very simple, standard way to program against the database. And because it is in memory and designed for in-memory residency above all, it's very, very fast. Provides microsecond response times and high throughput. Most Timesten customers use multi-site replication or even intra-site replication for improved availability and for disaster recovery. And this replication is actually very high performance. It's streaming and it's parallel. So using replication does not cause any performance impact, which is why I would say 90+% of Timesten customers do use replication. This deserves a separate slide. About half of Timesten's customers use Timesten as a standalone database. But the other half use Timesten as a cache against the Oracle database. And they do this because by bringing some selected subset of Oracle database data into the application tier, into Timesten, that application can benefit from in-memory response times. And that data is also fully persistent. So you don't lose that application data if you have a failure of any component. And there's multiple ways of caching data. I'm not going to cover all of them. But basically, there are two canonical types. You can have read-write caches. Read-write caches are where the transactions run against the Timesten database first, and then are propagated to Oracle asynchronously. You can also have read-only caches where the transactions run against the Oracle database, and the changes get refreshed into Timesten. And this gives you not just performance, but also high availability and additional fault tolerance. If the Oracle database has a temporary outage, you can keep running with the cache data in Timesten, for instance. And it's very helpful for also planned upgrades of Oracle. You can take Oracle offline, upgrade Oracle software, but your application keeps running because it can run out of the cache data. The next generation of Timesten, which was just released, is a scale-out version of Timesten. Scale-out Timesten was essentially a new scale-out architecture developed for these extreme OLTP applications like IoT and clickstream and billing and telecom billing and so on. It is designed to be high performance and highly available. So all data is duplicated. All nodes are active. And as everyone knows, there is no pure workload anymore, pure OLTP, or pure analytics for that matter. Most workloads are mixed or HTAP in nature, where you have both analytics and OLTP coexisting. So Timesten Scale-out does also offer very sophisticated SQL so that you can run reports against your real-time data. And one big difference between Timesten and the classic enterprise databases is that it's very, very easy to use. Literally from downloading the installation of Timesten and installing Timesten, bringing up a scale-out database, and running an application takes less than 15 minutes. And that's something you can't say for most enterprise databases, which is why Timesten is used very widely excuse me, in the embedded business, because it's easy to embed and very easy to operate. Sorry, I have a slightly scratchy throat today. Okay. So this is just repeating some things I said earlier. It appears as a single database to applications. You can add and remove nodes, and the data is automatically redistributed. And you can, new nodes automatically co-opt some of the data. If you drop a node, the data moves away to the other existing nodes. The nodes are duplicated, so if you lose any node, you can keep running. And the goal has been to keep it a strictly compatible subset of Oracle in terms of functionality, so that you don't have to relearn a new way to develop applications against Timesten. If you have an Oracle database, using Timesten is very, very simple. The same data types, compatible SQL, PL SQL, and the Oracle interfaces like OCI and JDBC. Now, this is all about making things go fast. That's the whole purpose of Timesten. So how fast is it? So I think Sam covered this yesterday in his talk, for those of you who were there. But I'll just repeat some of the numbers that I think he presented yesterday. Is Sam in the audience today? He's in the booth. OK, all right. Anyway, so I'm going to show you performance numbers which increase. As you know, for any scale-out architecture, writes are more expensive than reads. So the smaller the proportion of writes, the bigger the performance number. So for the WISE CSP benchmark, which is a fairly standard benchmark nowadays for these simple OLTP applications, for a 50-50 workload read-write ratio, we get 6.4 million operations per second. which is actually higher than anything we have found, at least in online disclosed numbers. It's an extremely high number for this workload mix. If you move to a 95 read, 5% write workload, then the number goes up to 38 million. And you can see that, as the write component goes down, you get a higher peak throughput for the application. And for a read-only version of YCSB, you get an astonishing 65 million operations per second. And this is running on a 16-way scale-out cluster where each node has 2 copies. So it's actually not that big of a system. It's a fairly achievable system. I mean, and most customers do not need performance this extreme. So somebody running a 4x2 would be very happy with getting 19 million ops per second. Now, Timesten has its own benchmark. We call it the Telecom Provider Throughput Benchmark because Timesten's original customer base was telecommunications. So in the telecom world, each transaction operates on a very small amount of data at very high volume. And this benchmark models that activity. It's actually shipped with the product for the last 10 years. So on this benchmark, we were able to achieve 144 million operations a second on an 80-20 read-write mixed workload on a larger cluster with 64 elements in the cluster. So 144 million per second was, again, higher than anything we have achieved before with Timesten. And if you think that's impressive, when you get to a read-only workload, this is just to, as a proof of concept, how fast can we possibly go? You can get to 1.2 billion SQL statements per second on this architecture. And I think this is actually a world record. 1.2 billion distinct SQL statements processed by a single database. I don't think there's any other system that can do that. You can certainly get that many rows processed per second, as I'll show you next. But as far as distinct SQLs processed and executed and returned to the application, this is a very high number. OK, so that's Timesten. And it's really for latency critical custom OLTP. Let's move into the database tier, where we have database in memory, which is designed really for real-time analytics by providing the ability to process data at the rate of billions of rows per second. It also allows faster mixed or HTAP workloads, because if you make your analytics very fast, you can drop analytic indexes and also speed up your transactions because there are fewer indexes to maintain. So this is sort of a well-known fact in relational database design, that if you have a transactional system, you really want a row-based architecture, because transactions work better when you have a row format, because you can go directly to your rows, get your work done, and get out. On the other hand, if you have an analytics workload where you are looking at a lot of data, you're typically scanning a subset of columns and looking at all the rows. There, you're better off keeping your columns as contiguous units that you can scan and process quickly. But the state of the art has been so far that you pick one of these formats, and you deal with the benefits as well as the trade-offs. That's been the state of the art. And Sybase IQ is one of the first commercial vendors of columnar stores in the 90s. But they really didn't work well for OLTP. They were really meant for analytics workloads. So this is what we would call a controversy. So what is a controversy? A controversy is a discussion where the thing that dominates is the expression of opposing views. And of course, there's no shortage of controversy today. If you look at the news, all you see is controversy. But it doesn't compare with this controversy that's been running for the last 50 years or more. Whose turn is it to get shot today? Is it Bugs Bunny's turn or the duck's turn? And this debate, as far as I know, has not yet been resolved. It's an ongoing controversy. Again, in the database world, there's been a very similar controversy. Do you want the row format, or do you want the column format? It's a controversy without any semblance of convergence. SAP HANA says you need to have the column format for everything. That's the only thing that makes sense. And others have said, no, if you do that, you can't really run transactions well. So that's the controversy in the database world. So we decided to address this controversy, saying, look, this is stupid. This argument doesn't make any sense. Let's use both formats, because they're both good for their intended uses. Let's use the row format when you're running transactions. Let's use the column format when you're running analytics and do it for the same data. So these in-memory images can exist for the same data to enable both fast analytics and fast transactions against the same data at the same time. And they're simultaneously active and consistent. So if no matter which format is used, you get the same results. The in-memory column format is purely in-memory, in database in-memory, and the benefit from that is that it is cheap to maintain. You don't have to modify indexes or any on-disk structures, so OLTP runs faster with this format compared to using a lot of analytic indexes. And because it is in-memory, it doesn't affect the on-disk format, so it's application transparent. Now, one important thing is that you don't have to put the whole database into this in-memory column store. You can pick whatever subset you want, because there's no point putting last year's orders, which you're not looking at, into memory, because you're not processing that data today. So you can select a table partition or a subpartition or a table space. You can, if you want, put the entire database in memory if you have enough memory, but you don't need to. So it's flexible and lets you select what you want to have in memory. And so what do we get by doing this? The big benefit by having the column-based architecture is that you can run something called SIMD vector processing. Because you have all of your operands together in memory, you can process multiple values in one instruction. And you can actually see a demo at the Oracle booth outside, where we show you how this vector processing can give you billions of rows per second scan speed, while the row format, no matter how efficient it is, can never really exceed some millions of rows per second in scans. So for instance, looking for all the sales in California, you can just scan the California column, look up multiple values in parallel through these SIMD vector registers, which Intel provides through an instruction set extension called AVX. And that lets you run your scans even 10x faster than you could by not using vector instructions. And that's why this can provide you with billions of rows per second scan performance. It's actually a very powerful technology, especially when combined with compression, since each of these values can be then encoded as a small value in a dictionary. Instead of the full value with a state name, you can use a small 5-bit, actually, dictionary value that you can then compare in parallel to the value for California. So this is the heart of the in-memory columnar technology, that you can get very, very fast scans. You can also process data for joins more quickly. And the reason this is possible is because scans are so fast, you can sort of convert joins into a series of scans. Like if you're looking for sales in outlet stores, you can look at the stores table first and find out the list of stores that are actually outlet stores, build that qualifying list, and then scan the fact table for qualifying entries where the store ID matches one of these outlet stores. And that can be done again through SIMD vector processing. And we use a technique called Bloom filter that I won't go into the details of, but that basically lets you do a very, very fast scan and filter to reduce the fact table data and basically making the join happen without really doing a join. So this gives you 10x faster joins. The same technique can be applied to more complex scenarios. Most analytic workloads require reports, which look at multiple dimension tables and have multiple predicates and multiple aggregations. The same idea in this example, if I'm looking for sales of footwear products from outlet stores, I would first scan the dimension tables, build an outline where each cell corresponds to an outlet store and a footwear product. So I first build that outline, and then I scan the fact table. And for each fact row, where the row looks like the row matches a footwear product and an outlet store, I increment the corresponding cell in the outline. So as I scan the fact table, I can do this aggregation in real time. Now, this is a very simplified, oversimplified description of the algorithm. We call it vector group by. But it does let you run aggregations 10x faster without having to predefine materialized views or cubes like many systems require. So you can get fast scans, fast joins, fast reporting. How about scale out? So database in-memory gives you the ability to scale out your database to any size. You can run your column store across multiple nodes. We have two scale-out technologies in Oracle. One is called RAC, Real Application Clusters. The other one is sharding. Either way, you can take a column store and spread it across multiple nodes and get the benefits of multiple host CPUs so that you're not limited by the memory on one machine to run your column store. Now I'm going to move to the storage tier. And natural question is, why would you have in-memory and storage? They're sort of contradictory concepts. And the answer is, well, because storage is now actually has a significant amount of memory in it. And we have done a lot of in-memory optimizations inside the storage tier for Exadata. So anybody here familiar with Exadata as a concept? Very small number, OK. So I'll give you a very brief Exadata primer. It is Oracle's ultimate database platform. It has unique hardware designed to run Oracle database, both on the compute side for database processing and on the storage side for running storage operations. It has a lot of database software, each point in the stack, specialized algorithms that benefit OLTP analytics and consolidated workloads. And the reason it's used a lot by large organizations is that it provides full stack automation. It automates a lot of common operations that people have to go through, and it gives the customer one number to call if anything breaks. So it's a very powerful tool to run your business, and it's one of Oracle's fastest growing markets. It's been around for 10 years. Actually, we just had the 10th anniversary last week. What's interesting about Exadata is that we found that there was a unique issue that was being caused by flash. As you know, storage now is no longer spinning Rust. It's mostly flash. Now, flash creates a gigantic problem. The latest flash cards are very, very fast. They're very high bandwidths. Okay, and the storage area network bandwidth hasn't really gone up as much. In fact, you could max out a single SAN link with one flash card. That's how bad it is. So if you look at storage arrays, like an IMC storage array with 480 flash drives, it can't deliver more than 30 gigabytes per second because of bottlenecks in the network. It should be able to get 2.6 terabytes per second to deliver all that bandwidth, but it can't because there's a choke point in the network. So what we had to do in Exadata was the following. We had to offload queries to run on storage. We had to offload query functions so that we could process data at their source, running against local NVMe flash, rather than having to aggregate data at a higher level. We had discovered, basically, that you can't really scale performance with a shared storage array, but you can scale capacity. So if you really want to scale performance, you have to move the compute to storage. And this is an issue that you cannot solve in the database alone or in storage alone. It has to be done in both places. The database has to see a query, say, hey, this query is going to scan 1 billion rows. I better push some of that scan to the storage cell and get that reduced data back before I do anything on compute. So this requires intelligence in both tiers. And Exadata X7, the latest generation, its total flash bandwidth is very high. It's comparable to memory. It's 350 gigabytes a second. So flash requires query offload for high performance, to maximize bandwidth. In order to get the most out of flash, we push that in-memory column format into flash. This lets us run that scan against flash on the storage tier with the same benefits the scans get on the compute tier. So all the SIMD vector processing, all the other optimizations we have in compute, they now run in storage as well. And this effectively gives you a big boost because flash is a lot cheaper than memory, and there's a lot more of it on systems. So on the X7, for instance, you can have hundreds of terabytes of flash capacity. So effectively, it's like getting a column store that's hundreds of terabytes in size. And with this new in-memory format running on that flash tier, we run these offloaded queries. We call them smart scans, or there's a variety of names for them. But let's call them offloaded queries, up to 10x faster. Unlike the in-memory column store, where you still have to declare what you put in memory, this doesn't require any user intervention. This is completely transparent, automatic. Oracle just released a cloud service called the Autonomous Data Warehouse that basically runs because of this. Because these offloaded queries are so fast, the user does not have to create any indexes or views or anything like that to accelerate the workload. So it sort of powers autonomous warehouse by enabling super fast offloaded query processing. OK, so that was a very, very quick flyby of in-memory at Oracle. It is a cross-tier technology. It's not just one tier: application, database, and storage. Every tier needs in-memory optimizations. Oracle was given a nice accolade by Forrester last year, because Forrester liked the fact we had multiple technologies for in-memory, such as Timesten and database in-memory. And they put us ahead of everybody else in the Forrester wave. I'd like to leave you with one thought. As practitioners in this space, we're all friends and partners and family here. We're in-memory practitioners. We've got to sell this vision to customers and other practitioners. In-memory is important because it enables a real-time enterprise. And that's the only way to be profitable in the future. So please take this back with you. Use this if you have any skeptical audience members saying, who needs in-memory? Flash is fast enough. I can just run without any in-memory optimizations using a buffer cache. Tell them it's not true. You will not get the response times you get from in-memory by taking a disk-based architecture and running it against fast storage. You need to do more. So if you want to be data-driven, agile, and efficient, the three elements of a real-time enterprise, you have to embrace in-memory technology. So that's all I had to say. Thank you very much.